Today, we want to look at two-dimensional surfaces in R3. We want to talk about how we can take an equation and picture what it looks like. And we're going to start with one. Actually, I can't remember what I talked about yesterday. We're going to start with a new one. We're going to start with a nice simple circular paraboloid. If you're thinking by the name of this thing, that's going to be some kind of combination of circles and parabolas, you are correct. The oid part is the part that's telling you that we're dealing with an object in 3 dimensions. And this is just going to be a surface. And we're going to start with the easiest circular paraboloid. Z is x squared plus y squared. We want to start with this so that we could see how, because we'll easily be able to picture what this looks like. And we want to see how we can break this apart. We always want to start with an example that we know what the picture looks like, so that we can take our method for analyzing what it looks like and know that the method works. Always do the new process on a problem that you already understand. Like when you learn integration, you want to learn integration by finding areas of rectangles, even though we already know areas of the length and width. You want to use your integration process to find the area of a circle, even though you already know it's pi r or something. Even though you already have that information, you want to make sure that the method that you're developing works on something that you already know. Then you can take it to things that you're not familiar with and practice analyzing them. So let's start with something nice and straightforward, a circular paraboloid. This is unsurprisingly going to look like part circle and part parabola. So we're just going to draw it over here. There's the circle parts. And there's that parabola parts. Down here at the bottom, we're going to have a vertex in either direction. And that vertex is going to be sitting on the origin. I'm going to do the normal thing where the y goes to the right. X is going to come straight out the board. And z will be up and down. So the object that I drew here is clearly only a 2-dimensional thing because I drew it on a flat surface. But it's supposed to be a 2-dimensional representation of a 3-dimensional thing. We want to see that circle that I kind of didn't draw perfectly round as being at a 3/4 view. So we're standing some positive x, some positive y, and it looks like some positive z, and we're looking down towards the origin at this object, just kind of bowl shaped. What we want to be able to see, make sure we see, is that it's circles wherever I slice this horizontally, that is, slice it parallel to the XY plane, we're going to be looking at a circle. When we look at slices parallel to the XY plane, we're going to get circles. We need to be able to see this in the equation as well. We need to be able to see these circles in the equation as well. So notice that when I take a slice parallel to the XY plane, I'm looking at a fixed value for z. I'm picking some number. This one looks like it's maybe 1 unit above the XY plane. That's where all the values of z are the same. So slices parallel to the XY plane are circles. That's where all that's where the z is going to be constant. So parallel to the XY plane, that's going to tell us that z is constant. That's the parallel to the XY plane part. If z is constant, we need to be able to see that in the equation as well. And we'll have x squared plus y squared is equal to some constant. So our equation will look like x squared plus y squared equals z, which is constant. So it'll look like x squared plus y squared is equal to some constant. I use k, the mortal constant. Now, in the picture, we see that slices parallel to the xy plane are circles. We can see in the equation that slices parallel to the xy plane are circles, because x squared plus y squared equals constant. It's a circle centered at the origin with the radius the square root of k. We see the circle in the equation. We see the circle in the image. Any questions? If we look at different values of the constant z, I just get larger circles. And we can see that in the picture. Down here at the origin, we've just got the points. If z is equal to x squared plus y squared and x and y are both 0, then z is equal to 0. We're way down here at the vertex. If we move 1 unit up, we're looking at a circle of radius 1. If we move 2 units up, we're looking at a circle of radius square root of 2. If we go up to 4 units, we're looking at a circle of radius 2. So we can imagine these circles as z gets higher, we can imagine these circles. And so that's going to give us an idea of what a contour diagram should look like. So let's think about a top view and think about many different level curves. So if we think about looking down at this circular paraboloid from the top, we're going to draw a level curve. We're going to take a fixed value of z and we're going to draw what that curve looks like. Draw the circle first. Yeah, I'm going to have to draw a bunch of concentric circles, so it's going to be a mess. But if we look down from the top, the first thing we see, I'm going to put our x and y axis in the normal way we orient things. So here's a top view. And I'm going to draw the circle that I see when z is equal to 1. That's going to be a circle with a radius of 1. That first one is going to be our circle of radius 1. Now I'm going to look at another level curve. I'm going to make the level curves 1 unit apart. So now I'm going to pick z is equal to 2. So my equation will look like x squared plus y squared equals 2. So we're going to be drawing a circle with the radius square root of 2. So this circle is going to be a little bit closer to our circle of radius 1, because the radius is going to be like 1.4. So if this is 1, and then that would make this 2, here's our second level curve. There's our circle of radius 2. So our first circle is a radius 1. Our second circle, where z is equal to 2, is at a little bit closer. So it's got a radius of 1.4. When z is equal to 3, we'll have a circle with a radius square root of 3. I just said square root of 2. So what we're going to notice is that the circles are getting closer together. So what we want to notice is that the circles are getting closer together. When z is equal to 1, we had a radius of 1. The next one was 0.4 units away. The next one was 0.3 units away. The square root of 3 is about 1.7. And then when we get to z equals 4, we'll have a circle of radius 2. So what we want to notice is that our level curves are all circles, and as z increases, we should see the circles getting closer together. Even though the values of z are increasing just by 1 for each level curve, the circles are getting closer together. This indicates that as z gets higher, the sides of our surface are getting steeper. So as the circles are closer together, that means the sides are getting steeper. So that's showing us that the sides of the paraboloid are getting steeper. So if we come along across this picture on, say, a topographical map, we can see what's going on. The numbers would indicate, since it says there's a 0 down here, then a 1, 2, 3, and 4. Since these level curves are getting steeper, the farther we get from the center, the steeper that this hole is going to get. It'd be like looking out this window. We could see there's this very steep hillside. And so the change in elevation from the bottom floor of building 8 to where that parking lot is the same as say the bottom floor building. What is that one of the automotive one? Is that 11? Anyway, from building 11 up to that height, it's further away. It's not as steep when you're over by the automotive area. But over here, the contour lines are going to be very close together because that's a pretty steep hillside. This is just a way for us to communicate a third dimension with only two, because we need to make a map that people can roll up, or fold up, or display on our primitive two-dimensional screen. Any questions? Comments? So we want to see these circles, these level curves, getting closer together and indicating that the paraboloid is getting steeper as z increases. So we see that slices parallel excuse me, to the xy plane are going to be circles. These are going to be slices where z is constant. Let's slice parallel to another plane. If we slice parallel to the xz plane, we look at slices parallel to the xz plane, we're going to get parabolas. Slices parallel to the xz plane are parabolas. We can imagine building this paraboloid by taking that parabola and just rotating it about the z-axis. But we're thinking about slices parallel to the xz plane, and those are parabolas. If we look at values that are, if we look parallel to the xz plane, we got to figure out what is constant. When the slices are parallel to the xy plane, that's where z is constant. So if I have slices parallel to the xz plane, what's constant? So when we look at slices parallel to the xz plane, we can see from the picture that they're going to give us parabolas. Since we're slicing parallel to the xz plane, we're going to look at all the places where y is equal to constant. The xz plane is where y is equal to 0. Then if I make a slice parallel to that, say where y is equal to 1, that was actually the whole thing. If I slice parallel to that, like where y is equal to 1. So if we look at y as constant, we can put that into our equation, z is equal to x squared plus y squared, and see what kind of shapes we get. Although I ran out of space. So if y is constant, then our equation will look like z equals x squared plus k squared, where k is just a constant. I need to connect my y is constant. We'll just do a portal. So here we see the parabolas that we'll be looking at. When y is equal to 0, we just get the parabola z equals x squared. If y is equal to 0, then we get the parabola z equals x squared. That's going to be a parabola opening up with a vertex at the origin. And that is what we're looking at. This green parabola right here is z is equal to x squared, vertex at the origin. If I move 1 unit over to where y is equal to 1, we get the parabola z is equal to x squared plus 1. That's going to be a parabola opening up with a vertex at 0, 1. And that's going to be the parabola next to this green parabola. We can see that since this side sweeps up, we're going to get a parabola and the vertex is going to be above the xy plane. And so on. And if y is equal to 2, we get the parabola z is equal to x squared plus 4. Notice that this is showing us the sides are getting steeper as well. We're taking equal steps away from the origin where y is equal to 0. We go from y equals 0 to y is equal to y equals 1. And the vertex has gone from 0 up to 1. But when we take that same step from y equals 1 to y equals 2, the vertex goes from a height of 1 to a height of 4. It's going up higher in the same step. That means things are getting steeper. And it gets steeper still the further we go out. If y equals 3, we get the parabola x squared plus 9. So once again, we can see this side, as y increases, we can see the side of our surface getting steeper. The side of the surface is getting steeper as y increases. And that's exactly what we drew. We drew a bunch of circles, and it gets steeper as we go up. Any questions? Too simple? We're expecting more out of your calc 3 class. I told you this is the easiest of the calc classes because you've already got your mechanics and your thinking installed. You already know about thinking about infinity. We're just going to try to apply calculus thinking, different things. This same analysis, we can just turn 90 degrees and look about what happens when x is positive. But what we are doing is we are looking at level curves so that we can create two-dimensional representations of three-dimensional objects. We can do the same thing with all these parabolas. But the circles were getting so shaky, I didn't think I could draw a bunch of parabolas. And I was going to run out of space because it gets pretty steep. I have to get a 1, a 4, and a 9, and a 0. And that's just too much to fit. But we can see all these parabolas. That first one would be a parabola with the vertex at the origin. The next one, when y is equal to 1, the parabola is 1 unit higher. The third one, where y is equal to 2, the parabola is going to jump up 3 units from that. And then the fourth one, where y is equal to 3, the parabola is going to jump up 5 more units. Any questions? Comments? Snide remarks? Deep thoughts? Right now, everybody's thinking, he is recording this, right? Like, oh man, I could have slept in and just watched this later. We're all having that regret. Oh man. Here's an important thing to know. Here's why I'm glad that you're here, even though you might be unhappy to be here. This is the beginning of the semester, and in the beginning of the semester, we have a high level of a drug that I like to call motivation. Right now, it's the beginning of the semester, we've got motivation. It's not only the beginning of the semester, it's back to doing school like we used to. And it hasn't truly set in how awful it is to commute somewhere if there's a way to not commute somewhere. But that's okay, because some of you have told yourself, this semester is going to be different. I'm not falling behind. I'm going to do my homework right away. I already know that that's not true, because I can see the grades in the grade book. I can see who hasn't started. So. But right now you've got motivation. So you might be telling yourself, I'm really going to stay on top of everything. I'm not going to skip class. I'm going to make sure I do all my stuff all the time. You need to know that if you're telling yourself that, because on a certain level, it's not true. You're telling yourself that because you know you have to tell yourself that. And you're just, the question really is, how much are you going to follow through with that promise you made to yourself? You know what I mean? Here's what you need to do with the motivation that you have now. Motivation is a terrible friend, because motivation is going to fail on you when you need it the most. Here's what you use motivation for, and why it's okay to have it now. Motivation can lead to habit. Habit, that's more of a neutral thing. It can be a good friend, it can be a bad friend. But if you take your motivation and build the habit of showing up to work every day, and build the habit of doing your work every day, then on the days where motivation has fucked off, you'll be like, oh, man, I do not see myself going to school today. There's no way I'm going to school today. When you get out of bed, forget it. I just cannot stand listening to me talk about some more stupid math stuff. And you start watching. Just forget it. I am definitely not going in today. Motivation has left the building. I don't want to go to school. You get dressed. Forget about it. I am definitely not going to school today. You're in your car and you're on the way. And by the time you come to the full decision that you are definitely not going to school today, habit has already dropped you off in the classroom, and you might as well say, well, yeah, I'm here anyway. Habit will carry you through. Motivation is a dip and will fail on you when you need motivation the most. But habit is what gets you through the semester. So take the motivation you have now and start building habits. Go to work every day. Do your work every day. And just keep moving forward. Build that habit. Even if you don't think you have anything to do, if the day is over and you haven't done any math, then your day ain't over. Build a habit of finding a time to do some math, even if it's an assignment that you've already done. On a day where motivation is high, look at an assignment that you struggle with. This assignment was terrible and I struggled with it highly. But I have high motivation today. Therefore, I'm going to look at that assignment again and see if there's something else I was missing. On a day where motivation is not helping you, on a day where you're low motivation to get anything done, pick an assignment that was easy and review that one. Because if at the end of the day you haven't done any math, you ain't at the end of the day yet. You're trying to build a skill, you're trying to build understanding. That's an everyday thing. It takes just training and practice. And you can't make it up later. Think about Think about if you do an exercise routine at the gym. If you skip going to the gym all week, and you just go on Sunday and do 5 workouts over 8 hours? No, that's not how it works. You get hurt doing that. And the same is true in dealing with math. You're going to get hurt doing that. Probably not physically hurt, but there's kind of a significant amount of mental trauma that comes along with it. You know what I mean? Like sleep. You can't just make up sleep on the weekend either. You got to build a habit of getting a sufficient amount of sleep. Now I know y'all are engineers or engineering students, future engineers, and you think it's going to be okay to pride yourself on getting only 4 hours of sleep a night and making yourself suffer. That's stupid. You do need more than 4 hours of sleep a night. So get more than 4 hours of sleep a night. You know what I mean? How many of you work better under pressure? You need to know that ain't true. It is 100% not true. If you have 3 weeks to write a paper, spend the 3 weeks writing the paper. The problem comes from the fact that you've probably been rewarded for putting something off. You said, oh, I got to write a paper. You put it off for 3 weeks. You're like, oh, well, crunch time. You spend all night, you pull an all-nighter, you write a paper, you turn it in, and you get an A on it. Congratulations, you just reinforced a bad behavior. You just got reinforced for putting the paper off. You know what I mean? And you get the behavior that you're going to reinforce. And so you start developing this belief. I work well under pressure. Now let's look at it from the other side. Look at the other reward we get for thinking that we work well under pressure. Paper's due in 3 weeks. If we say we work well under pressure and just plan on spending the last day on the paper, that's 3 weeks we get, not right up here. That is a big, fat reward. And your brain's like saying, oh shit, give me some of that. 3 weeks of not doing work, your brain is going to be all in. And it's going to say, you know what? You're really good at writing a paper at the last minute. So get the Xbox fired up. Yeah. Look at the reward that doing the work is competing against. You know what I mean? Your work product suffers when you just try to cram it all in at the day. So working well under pressure is a lie that you tell yourself. Ask me how I know, incidentally. I didn't read about this. This is my lived experience. And I'm saying, don't do what Donnie Don't does. In The Simpsons. Anyway, don't do that. Do your work right away. If you find yourself telling yourself this semester is going to be different, you need to recognize, unless you do something about it, this semester will not be different. I know what that refrain sounds like too. Also, you're going to tell yourself that you're good at multitasking. No one is good at multitasking. That's just another ill-advised behavior that's been reinforced. Any questions? All right, so I guess that's your true homework, not just to do math problems, but to build a habit of doing math problems every day, because you are trying to be better at math. I know that your actual goal as a student is to get through this class with as little work as possible. And I also believe in that. That's just good capitalism. Always, always do as little work as possible to get your tasks done. Don't do this extra stuff. If there's someone paying you and they're trying to convince you to do extra, they're trying to get your labor for free. Forget that. Do as little as possible. Did the work get done? Then off I go. You know what I mean? All right. Finish up chapter 12 this weekend. Learn some cool surfaces. We'll talk about some more surfaces. That's going to do it for today. That's going to do it for this week. I'll see you all on Monday. Everybody have a good weekend, and thanks for playing.
Started chapter 13 on Monday.